In the previous video, we looked at how to analyze data that were collected using a repeated measures design or a matched pairs design. In this video, I want to show you how to analyze data that comes from two groups. In this case, the groups are independent from one another. So unlike with repeated measures and matched pairs, where we obtain multiple scores either from the same individual or from a pair of units, the units in each of these groups are independent of one another. The best kind of design for collecting two groups of quantitative data is the two-group completely randomized design. A simple random sample of study participants is randomized to a treatment and control condition. The explanatory variable is the study condition, with the values control and treatment. The response variable is an outcome that is observed after the intervention. The response variable can be quantitative, for instance, a score of 53 points, or categorical, for example, a successful cure. The conditions must be independent of each other, and observations within each condition must be independent of each other. To help understand this design further, let's look at an example. This is an actual example from an actual study that was conducted with 42 medical residents who participated in a study of the effects of video game training with the Nintendo Wii on laparoscopic skill. First, each resident was timed at taking out a gallbladder. The residents were then randomized to a control and treatment condition. Those in the treatment condition played on the Nintendo Wii 1 hour per day, 5 days per week, for 4 weeks. Those in the control condition were asked to refrain from video games during these 4 weeks. The response measure was the decrease in time, measured in seconds, to remove the gallbladder. I'm not so sure if I was the patient that I would think that removing my gallbladder faster is a good thing, but nonetheless, that's what they were measuring in this study. So the explanatory variable here is whether or not they play video games. Notice that some of the residents were given video games, the others refrained from video games. The response variable here is decrease in time to remove the gallbladder. So we are looking at the relationship of an explanatory and response variable. And we are doing so with data from two groups, a treatment and control group. Here are the data. Notice we have two variables. The explanatory variable is condition. The values of that variable are either T for treatment or C for control. The response variable is time. This is measured in seconds, and a positive number indicates that there's actually a decrease in the amount of time to remove the gallbladder. What is the statistic that is of interest to us here? It is the difference in means between the treatment and control conditions. Generically, we can say we're looking at the difference of the mean of group 1 and the mean of group 2. Now these means are for the sample. What we really want to know is the difference of means in the population, mu1 minus mu2. The difference in our sample means estimates the difference in means in the population. I would like a confidence interval for the difference in means in the population. In the past, when we created a confidence interval, we started out by looking at the sampling distribution of the statistic. Can we get a sampling distribution for the difference in means? Of course we can. We can get a sampling distribution for any statistic. This would simply involve taking a random sample, randomizing to two conditions, calculating the means in each condition, and then doing this again and again and again and again. Of course, we don't actually do that, but we theoretically can construct this sampling distribution. The sampling distribution is going to have a normal distribution because the central limit theorem applies even when we're talking about the difference in two means. As long as we have a big enough sample size, we know that the sampling distribution of the difference in two means is normal. What about the standard error? The standard error is computed with this formula. Notice that all we need is the standard deviation from each of our two groups, the standard deviation from the treatment group and the standard deviation from the control group. We're going to be squaring those and dividing each by the number of participants that are in that particular group. We take the square root of the whole thing, and that's the standard error of the sampling distribution of the difference in means. Now we also need a critical value in order to calculate μ to get a confidence interval. The critical value is going to come from a t-distribution with some degrees of freedom. What degrees of freedom? The formula for figuring out the degrees of freedom so that we know which t-distribution to use is quite messy. So we're going to let software figure it out for us. Once we have that critical value, we can multiply it by the standard error of the difference in means, and this gives us μ. We always get μ by taking the product of a critical value and the standard error. Once we have μ, we can add and subtract it to the difference in means, and that will give us the lower and upper boundary of a confidence interval for the difference in population means. Let's see this in action. I'm going to read in the data that I showed you, that is, the data from the gallbladder surgeons in residence, and then we're going to look at a box plot. Here are side-by-side box plots. Notice that on the vertical axis we have time improvement in seconds. So in fact it looks like playing video games did lead to faster gallbladder surgeries. The box plot for the treatment group is higher than that for the control group. Now if we want to obtain the individual statistics, we're going to have to take a subset of our surgery data. We need one group to be the control group and one group to be the treatment group. We do this using the subset function. I want to take the time, and I want to get that time separately for when condition equals C and when condition equals T. I'm going to store these in control and treatment variables. Now if I get a summary of control, I can get the 5-number summary plus the mean for the control condition, and I notice the mean is about 60. So even those in the control condition sped up by about a minute for their gallbladder surgeries. Let's also get the standard deviation while we're at it. And now let's get the summary for the treatment condition. The mean there is 133 seconds. That's over 2 minutes. So those who played video games were actually going to be 2 minutes faster on average when they did gallbladder surgeries. Let's get the standard deviation. And now to get the confidence interval, I'm going to use the t-test function, but instead of giving it a single variable, I'm going to give it the response variable as a function of condition. You may remember from past videos that tilde, which we saw when we were doing regression analysis, means as a function of. So I'm going to say I want a t-test for time as a function of condition. When we run this, we get the confidence interval. The confidence interval here ranges from -125 to -21. If we look at these box plots, we can tell that what the t-test function did here is it subtracted the treatment mean from the control mean. That's why we're getting negative numbers. We can turn this around and make these positive, from 21 to 124. We just need to turn around our mu's so that we're saying mu of treatment minus mu of control. So we have determined that if we take the mean of the treatment minus the mean of control, that's going to be between 21 or 125. Another way of saying that is, we know that the average increase for those in the video gain condition was between 21 and 125 seconds faster than for those in the control condition. So we have just looked at a graphical display for two groups, obtained summary statistics, and finally, and importantly, made an inference about the difference in means based upon these summary statistics.